Now let's say we are working on a model to classify our customers for loans. So our response variable shall have two categories, defaulters and non-defaulters. Now let's say we have predictors as gender, income, location, whether customer has a house or not, their food habits, and so on up to m variables. Now it's apparent to us that food habit has got no relation with a customer being a defaulter or not. So one way is that we eliminate this variable altogether. This is called as feature elimination. But the real life scenario is not that simple. First of all, there would be so many variables and we can't just draw a line saying that these are useful variable and these are not. Because we don't do this based on our whims and fancies. Secondly, by doing this, we are potentially losing information. We never know how a particular variable will interact with other variables and what will be its impact. So instead of eliminating the features, we use PCA. So what we do is, we don't remove the feature completely, rather we extract the features. What does it mean? It means that we use all the features and make linear combinations of it to create new variables. Now what do I mean by linear combination? Basically we create new variables that are called principal components, such that each of these variables are a linear combination of all the original variables, like so. Now you can see here, each variable is contributing to all the principal components. So we are not eliminating any variable. Instead, we have extracted information from each of the variable and captured it in principal components. This is known as linear combination of the original variable. Now these variables are ordered based on their importance. Now what I mean by importance is that these variables are ordered such that principal component 1 will explain our response variable the most. Then principal component 2 will explain after PC1 and so on. So based on how well they explain our response variable or based on the variability captured, they are ordered. After that, we can use some cutoff and select the number of features that are required for us. This way we have reduced the number of features and yet have retained maximum information from all the original variables. So isn't it a wise approach? I'm sure you would agree that this is a better approach than eliminating the features. Now let's see what is the definition of PCA. As I said earlier, PCA is a dimension reduction technique. A principal component is an orthogonal linear combination of the original predictors. And principal components are orthogonal to each other. It means that they are independent of each other or they are perpendicular to each other. Now as you can see in the left panel, we have our original data set. And then on the right hand panel, we have our principal components. What we are doing here is that we are projecting our original data set on principal component space. And the transformed data is called principal components, which is orthogonal to each other. Now this is an example of two variable case. We can extend this to n component space, but obviously we can't show it in the form of a graph beyond 3D. So I hope you have got the idea what is happening here. Now just to summarize, principal component analysis is a dimension reduction technique. And principal components are a linear combination of the original variables, which are ordered based on the percent of variability explained, or how well they explain the response variable. And then to create principal components, we project the original data into the principal component space, which in turn gives us the principal components, which are orthogonal to each other, as shown here in the left and right hand panels. So I hope this clarifies what principal component is.